Students, in this lecture I'm going to start a new topic, that is direct memory access controller, that is DMA controller. It is also called 8257. So in microprocessor based systems, data transfer can be controlled by either software or hardware. So data transfer means transfer of data from input output device to memory, or from memory to input output device. So for doing this we have used program instructions. So far for the microprocessor based systems we have used program instructions to transfer data from input output device to memory, or from memory to input output device. And to transfer data using this method, what microprocessor has to do, it has to fetch the instruction, it has to decode the instruction, and it has to execute the instruction. Only then the data used to get transferred from input output device to memory, and vice versa. Now to carry out these tasks, microprocessor requires considerable time. So this type of, or this method of data transfer is not suitable when we are supposed to transfer large data, such as data transfer from magnetic disk or optical disk to memory. In such situations, hardware controlled data transfer technique is used. So in this technique, an external device is used to control data transfer. External device generates address and control signals required to control data transfer, and allows peripheral devices to directly access the memory. Hence, this technique is referred to as direct memory access, and the external device which controls the data transfer is known as direct memory access controller, that is DMA controller. Now, how DMA controller operates in a microprocessor system, I have shown here in this. So DMA basically works in two modes, DMA idle cycle and DMA active cycle. So what is DMA idle cycle? When the system is turned on, means the switches are in position A, means all the switches are in position A. So the buses are connected from the microprocessor to the system memory and peripherals. I am talking about this buses. The buses, data bus, this is address bus, data bus, control bus. So these buses are connected from the microprocessor to the system memory and the peripherals. So microprocessor then executes the program until it needs to read a block of data from the disk. To read a block of data from the disk, means the peripheral device I am talking about. Whenever I am saying disk, means it means the peripheral device. So read a block of data from the disk, microprocessor sends a series of commands to the disk controller device, telling it to search and read the desired block of data from the disk. So when the disk controller is ready to transfer first byte of data from the disk, it sends DMA request signal to the DMA controller. This DMA controller. So it sends DMA request signal, that is DREQ signal, to the DMA controller. Then DMA controller sends an hold request HRQ signal to the microprocessor. Hold input. The microprocessor responds this hold signal by floating its buses and sending out a hold acknowledgement signal, that is HLDA signal, and it sends a control signal to change switch position from A to B. Now this disconnects the microprocessor from the buses, and now the DMA controller gets connected to these buses. So now the DMA controller gets connected to the buses as the position of switches have been transferred from A to B. Now the next is DMA active cycle. So when DMA controller gets control of the buses, it sends the memory address where the first byte of the data from the disk is to be written. It also sends a DMA acknowledge, that is DACK signal to the disk controller. That is DACK signal to the disk controller, telling it to get ready for data transfer. Finally, in case of DMA write operation, it asserts both the IOR bar and MEMW bar signals on the control bus. Asserting the IOR bar signal enables the disk controller to output the byte of the data from the disk on the data bus. From the disk on the data bus. And asserting the MEMW bar signal enables the addressed memory to accept data from the data bus. In this technique, data is transferred directly from the disk controller to the memory location without passing through the CPU or the DMA controller. So when the data transfer is complete, the DMA controller unasserts the hold request signal to the microprocessor and releases the bus by changing the switch position from B to A. All the switch positions get changed from B to again A. After getting the control of all the buses, the microprocessor executes the remaining program. So in this way, the data is transferred directly from this disk controller to the memory location without actually passing the CPU or the DMA controller. Now coming to the block diagram of direct memory access controller. So this is a functional block diagram of direct memory access controller, or you can say 8257. So this is data bus buffer. So it is a tri-state bidirectional 8-bit buffer. It interfaces the 8257. This is 8257. It interfaces the 8257 to the system data bus. This gets connected to the system data bus, that is microprocessor system data bus. So in the slave mode, it is used to transfer data. As I've told you that the DMA controller works in two modes, the DMA idle cycle and the DMA active cycle. So the DMA idle cycle is the slave mode and the DMA active cycle is the master mode. So in the slave mode, it is used to transfer data. This data bus buffer is used to transfer data between microprocessor and the internal registers of the 8257. And in master mode, it is used to send higher byte address, that is A8 to A15. Here I have written also A8 to A15 on the data bus. So again I am repeating, in the slave mode, this data bus buffer is used to transfer data between microprocessor, means these lines works with like data bus. It is used to transfer data between microprocessor and internal registers of 8257, and in master mode it is used to send higher byte on the data bus. So here the lines this D0 to D7, this D0 to D7, these are the bidirectional lines and they are connected to the system data bus. So when CPU is having control of system bus, it can access content of address register, status register, mode set register and a terminal count register. So all these registers are inside the 8257. So which means the CPU is having control of the system bus and it can access contents of all the registers of the 8257, and it can also program control registers of DMA controller through this data bus. Now next and the address bus, obviously here we can see the address bus 8 to A15 and there is A0 to A7 lines are also there. So the four least significant lines, that is A0 to A3, the four least significant lines are bidirectional. In the idle cycle, they are inputs and used by the CPU to address the register to be loaded or read, and in the active cycle, they output the lower 4 bits of the address for DMA operation. A4 to A7 are unidirectional lines. This A4 to A7 are unidirectional lines, and they provide 4 bits of address during DMA service. Now the next block that I am going to talk about is the read-write logic. This is the read-write logic. So when CPU is programming or reading one of the internal registers of 8257, that is when the 8257 is in the slave mode, the read-write logic accepts the input-output read, that is IO bar or IOW bar, IO bar, R bar and IOW bar signal, decodes the least significant 4 address bits A0 to A3, and either writes the content of the data bus into the addressed register or places the content of the addressed register onto the data bus. So again I am repeating what happens in slave mode. When DMA controller is working in slave mode, then this D0 to D7 lines, these lines work as data bus for transferring data between CPU and 8257. And in the slave mode only, using this IO R bar and IOW bar pin, 8257 gets to know whether CPU wants to read data or write data from or into the registers of 8257. And the least significant bits, this A0 to A3 bits, they are used by the CPU to address the register to be loaded or to be read. Now during the DMA cycle, that is when the 8257 is working in master mode, the read-write logic generates the input-output read and memory write, or input-output write and memory read signals, which controls the data transfer between peripheral and memory device. So here the IOR bar and IOW bar, what is the use of this means that I have now only told you, that these are active low bidirectional pins in idle cycle. These are input control signals used by CPU to read or write the control registers of 8257, and in the active cycle the IOR bar signal is used to access data from a peripheral, and IOW bar signal is used to send data to the peripheral device. Now the next block that I am going to talk about is this DMA channels, that is I will be talking about the DMA address register. So what is happening, this DMA channels, that is 8257, provides 4 identical channels labeled as CH0, CH1, CH2 and CH3. Each channel has two 16-bit registers. Each channel is having two 16-bit registers. One is DMA address register and another is terminal count register. Again I am repeating, each channel is having two 16-bit registers. One is DMA address register and another is DMA count register. Terminal count register. So DMA address register, it specifies the address of the first memory location to be accessed. It is necessary to load valid memory address in the DMA address register before channel is enabled. So this is the format of DMA address register. This is the format for DMA address register. Next is terminal count register. So the value loaded in the lower order 14 bits of the terminal count register specifies the number of DMA cycles -1 before the terminal count output is activated. Therefore, for n number of desired DMA cycles, it is necessary to load the value n-1 into the low order. So the 14 bits into the low order 14 bits of the terminal count register. So I'm talking about this. We need to load this value. This is the low order 14 bits of the terminal count register, and we need to load the value n-1 into this low order 14 bits of terminal count register for n number of desired DMA cycles. Now the most significant 2 bits of the terminal count register specifies the type of DMA operation to be performed. So it is necessary to load count for DMA cycles and operation code for valid DMA cycle in the terminal count register before channel is enabled. So if the two most significant bits T0 and T1 both are 00 means DMA verify cycle is being processed. Then if it is 01 then DMA write cycle, if it is 10 then DMA read cycle, if it is 11 then it is illegal. So I'll continue with the block diagram of DMA controller in my next lecture also. I'm ending this class here. Thank you.